Yeah, thanks for introduction. Also, thanks the organizer for inviting me to this wonderful workshop. Sorry that I cannot attend in person, so I'm very willing to. And also sorry that I changed my title a little bit to I think this new title will have a less overlap with our last speaker Chen Fan's results. So the new title is non-Bloch PT symmetry of non-Hermitian systems. So this is a brief outline. I will first introduce some background knowledge of non-Hermitian systems, and then I move to our main result about non-Bloch parity-time symmetry, both in 1D and higher dimensions. And we will see that the behavior in different dimensions is very different, and we have not fully understand all the phenomena yet. So in the standard quantum mechanics textbook, we are told that the Hamiltonian is always Hermitian, but there is an implicit assumption that the system is closed. For many open systems in nature, the effective description is not to use Hermitian Hamiltonian. In many cases, so for many physical systems, the effective description is to use non-Hermitian Hamiltonian. Here is a incomplete list of systems, which I copied from a very long review article by Vida and collaborators. The physical systems involve range-form, the classical wave systems, open quantum systems, and even non-equilibrium statistical physics. And so before going into our own work, let's briefly explain the meaning of the concept appearing in my title. So the PT symmetry or parity-time symmetry was pioneered by Carbender and Bloch in 1998. But it stems from a very early work by T.D. Lee and Xing Yang. And the non-Bloch is about a band theory, which is quite a recent concept. So first, let me briefly recall the concept from PT symmetry. So in about 70 years ago, Lee and Yang studied the problem of phase transition. The main idea is to introduce a complex valued chemical potential. So they studied the behavior of partition functions in this complex plane, and found that signatures of the phase transition, which can be described by the singularity in the problem. By the way, yesterday was Professor Xing Yang's 100th birthday, and recently there is a book published to celebrate his birthday, and our work to be produced has also been included in this book, which I feel very happy. And Li and Yang's work motivated other people to consider a very strange field theory with the imaginary coefficient. This I, the 5 to the third. This interesting field theory with the imaginary coefficient. And this again motivated Carpenter and Bolger to study this even simple quantum mechanical, not field theoretical, this very simple quantum mechanical problem with the imaginary coefficient. They emphasize that this Hamiltonian has a PT symmetry, which means that the Hamiltonian is invariant under the combination of parity or inversion and times the symmetry, which changes I to minus I. And they showed that, they proved that this PT symmetry guarantees that the energy spectrum of the Hamiltonian can be real valued in certain parameter regime. From Peter's side, there even simple model that can also display similar phenomena. So this is a Hamiltonian for a two-level system, which is non-Hermitian due to this I factor here. And this model also has a PT symmetry, which means that the complex conjugation of the Hamiltonian, and after doing this operation using sigma x, which is the inversion operator here, is equal to the original Hamiltonian. So this Hamiltonian does have this PT symmetry. So indeed, the Hamiltonian has real valued spectrum when the non-Hermitian parameter G is smaller than the Hermitian parameter kappa. So for small non-Hermiticity parameter, the energy is real value, which is often called said to be in the PT exact phase. And when the non-Hermitian parameter is large, although the Hamiltonian still has a PT symmetry, the spectrum becomes complex valued. So you see when G is bigger than kappa, this becomes purely, this E becomes purely imaginary. So the bottom line is that the PT symmetry Hamiltonian generally has two phases: the PT exact phase for small non-Hermitian parameter, and the PT broken phase with complex valued energy spectrum for large non-Hermitian parameter. So this G equals kappa is called exceptional point, which marks the transition from the PT exact phase to the PT broken phase. And later studies show that the inversion is not quite essential. The most important ingredient in this PT symmetry is the anti-unitary operation. So the P can be replaced by almost any other operation, which is of course a unitary operation. The T is anti-unitary. This anti-unitary operation is very essential. There are many interesting consequences of PT symmetry, ranging from unidirectional invisibility, enhanced sensing, chiral mode, conversion, and many others. You may read this very concise reviews, which contains many more examples about the significance of the potential applications of PT symmetry, which I do not have much time to introduce in this talk. And then next, I will introduce the meaning of non-Bloch. This is essentially about band theory. A band theory that applies to the non-Hermitian system, which is called the non-Bloch band theory. So the motivation was originally in the topological phase of matter. Probably everyone here already heard a few concepts from the topological state of matter. So this material often has robust boundary mode propagating at the edge of the system, but this edge mode was very robust, and they are dictated not by the details at the boundary, but by the bulk topological invariant. And this correspondence between the robust edge mode and the bulk topological invariant is called the principle of bulk boundary correspondence, which explains the robustness of the edge mode, which is not killed by the boundary impurity disorder, and in many cases also electron interaction. And in the absence of interaction, the topological state of matter is easily described in terms of the topological band theory. From the solid state physics, we know that for any given band, the bulk energy spectrum is almost the same, whether we take periodic boundary condition or open boundary condition. But sometimes for the open boundary condition, there are topological edge mode. So this topological edge mode is predicted from the bulk topological invariant, which is defined using this Bloch wave function coming from diagonalizing the Hamiltonian in the Brillouin zone. So the original question is how to generalize it to non-Hermitian system, and we can do this by considering some very simple models. For example, the non-Hermitian SSH model, or its variation. We may introduce some non-edge coupling to this SSH model. So this may enrich the problem, but the essential idea is similar. The main point is that the Hamiltonian is non-Hermitian. The hopping is non-reciprocal. The hopping from the right to the left is different from that from the left to the right. And the difficulty in generalizing the topological concept from the Hermitian to non-Hermitian system is the following. If we diagonalize the Hamiltonian with periodic boundary condition, we get this blue energy spectrum. But if we diagonalize the Hamiltonian under open boundary condition, we get the red one. So these two energy spectrum looks very different. So this is very different from what we see in the Hermitian system. For Hermitian system, the bulk energy band should be similar, which is independent of the boundary condition. But here, the bulk band differs very much between these two boundary conditions. If we start from the standard band theory, the Bloch band theory, we can only get this blue point, this blue energy spectrum of the periodic boundary condition. The reason which was later found is the non-Hermitian spin effect, meaning that the eigenstate of the Hamiltonian are generally localized at the boundary of the system. So in most cases, almost all the boundary, almost all the eigenmode of the Hamiltonian are localized at the boundary in a exponential way. So it has exponential decay to the box. This may look strange at first sight, but this is allowed by non-Hermiticity, because for non-Hermitian Hamiltonian, the eigenmode, the eigenstates do not have to be orthogonal to each other, so they can stay very close to each other. So this is possible, and this indeed happens here. So this non-Hermitian scale effect means that the conventional Bloch wave picture fails for general non-Hermitian systems. So the next question with this non-Hermitian scale effect, the question is, how can we calculate the energy spectrum for a more general band theory? So we want to calculate energy spectrum under arbitrary boundary conditions, including the open boundary conditions, of course. And this cannot be done in the conventional band theory, which can only produce this blue energy spectrum of periodic boundary condition. So the key concept was the generalized Brillouin zone. So to explain this concept, it's more convenient to use this notation beta, which is a phase factor. Here, this K is our very familiar wave vector in the Brillouin zone. So this beta is a phase factor, which is e to the ik. So the conventional Bloch wave e to ikx can be written as beta to the x, with the modulus of beta equal to 1. So which means that it's a pure phase factor. So this gives us the conventional Bloch wave. Now we have non-Hermitian scale effect, meaning that the eigenmode are localized at the boundary of system. So we should not have beta modulus to be equal to 1. So we remove this beta equal to 1 constraint, which and allow this modulus of beta to be different from 1. And this gives us a generalized Brillouin zone. But to have a useful theory, we have to know how to calculate this generalized Brillouin zone. So if we do not have an equation which tells us how to calculate it, it will still be quite useful. So to derive this equation, we of course we have to use the boundary condition, and we succeeded in some special case, actually in the simplest case, and later the general case was done by Yokomizo and Murakami, and further generalized by Chenfang and collaborators. I think I will not go into details of this derivation, which is quite complicated. The basic idea is the basic result is the following: we have this characteristic equation, which means that given an energy E, we have several different beta values. And we can order these beta values by their modulus. And if we include the boundary conditions, then we have a very complicated equation, which looks this. This looks quite simple, but I hide all the complexity in the coefficient. This A1 and A2 are very complicated quantity, which is very difficult to solve when A is large. But very fortunately, this equation can be greatly simplified in the large L limit. When L is very large, this very complicated equation becomes very simple. The equation is that the middle two modulus are equal to each other. And this simple equation gives us the generalized Brillouin zone. We solve this equation, and this gives us this curve in the beta plane. And this curve plays a role for what the Brillouin zone does in the Hermitian band. So we call it a generalized Brillouin zone. For example, from the generalized Brillouin zone, we can read the profile of the eigenstate. For example, for the present model, under the given parameters, we have all the generalized Brillouin zones are located inside the unit circle, so which means that the modulus of beta is less than 1. So this means that all the eigenstates are localized at the left end of the system. So we can also calculate the energy eigenvalue from the generalized Brillouin zone. We just diagonalize the Hamiltonian in the Brillouin zone, in the generalized Brillouin zone, and we get the eigenvalues, and this gives us this energy spectrum, which we wanted very much. And this is the main idea of the so-called non-Bloch band theory, which is based on the generalized Brillouin zone. And the conventional Bloch band theory based on the standard Brillouin zone, which is beta modulus equal to 1. And with this generalized Brillouin zone, we can define topological invariant not in the standard Brillouin zone, but in the GBZ, the generalized Brillouin zone. And indeed, this gives us a correct prediction of topological edge mode. And this have also been confirmed in several experiments. And there are many subsequent work progress along this direction, which I have to skip due to limitation of time. So I will focus on the one aspect of this non-Bloch idea. It's called non-Bloch parity-time symmetry, or non-Bloch PT symmetry. So the idea is very simple. So the PT symmetry is about the reality of the energy spectrum. It tells us it's concerned. So we are concerned about whether the energy spectrum is real valued or complex valued. But what we care most is the physically observable OBC system with open boundary condition. So this red spectrum with OBC is more important to us. So natural question is how to predict when the spectrum is real valued under this open boundary condition. So as I have said, to calculate this OBC energy spectrum, we have to use the non-Bloch band theory, not the conventional Bloch band theory. So under this non-Bloch band theory, we should have a new PT symmetry, which is very different from the conventional Bloch PT symmetry based on the Bloch band theory. So this concept was proposed by Longi in a series of papers. The main point there is that this symmetry is defined on the generalized Brillouin zone, and here this beta is defined in the generalized Brillouin zone. So if we take the modulus of beta to be equal to 1, then this identity, this symmetry is not valid. So we have to take beta to belong to the generalized Brillouin zone. So this tells about the energy spectrum, the behavior of energy spectrum under the physical boundary conditions. So we have already seen an example which I show again here. So this is the PT exact phase with real valued energy, and this is the PT broken phase with complex, with some of the energy values taking complex values. And stimulated by this Longi's proposal, and we carried out the experiment to confirm the picture. The leader is Professor Peng Xue from Beijing, and so this is done in the experiment based on quantum walk of single photons. So maybe all of you know about the classical random walk. In the classical random walk, a particle moves in a single random path, but in a quantum walk, the particle is quantum mechanical, so it can move simultaneously along many different paths, and this path can interfere with each other. So this gives us the quantum walk, and we construct the following non-Hermitian quantum walk using single photon. It's non-Hermitian because there is photon loss, and this is the key ingredient which causes the system to be non-Hermitian. And I think I will skip other features of this operator, which describe the time evolution of the photons. The key ingredient is that this is a non-Hermitian system because the particle loss. So before the experiment, we theoretically calculate this energy spectrum under different boundary conditions. Under the periodic boundary conditions, the energy spectrum is generally complex valued, but under the open boundary conditions, the spectrum can be real valued in certain parameter regime, and it becomes complex valued, and the imaginary part becomes non-zero when the parameter, one of the parameters, theta 2, change to a higher value. we also confirmed that this PT symmetry is related to a symmetry in the generalized Brillouin. Here, the generalized Brillouin is a circle, but it's not a unit circle. The unit circle is dashed circle, and this generalized Brillouin is a smaller circle. And in the experiment, we initiate the photons at some point from the system, and then we observe the wave function norm, and this wave function norm, the non-time behavior of this wave function norm is dictated by the maximal imaginary part of the energy spectrum, and this wave function norm can be observed by counting the photon number. So the photon number is proportional to the wave function norm. So we can check the surviving photon number in the experiment. So in the PT exact phase, the corrected photon number saturates or slowly decay in the non-time limit. But in the PT broken phase, when the imaginary part is non-zero, it has an exponential growth in time. So we can observe the transition from the PT exact phase to the PT broken phase by counting the photons in the experiment. So indeed, we found that this PT symmetry breaking occurs at some parameter values, and this exponential growth indicates the PT broken phase. For this parameter, there is no exponential growth of photon number, so this is the PT exact phase. And when we submitted this paper to PIL, then one of the referees asked us whether this PT symmetry breaking has signatures in the has some direct signature in the generalized Brillouin zone, for example, from the shape of the generalized Brillouin zone. So when asked about this question, we very quickly answer that the answer is no. So the PT symmetry can be calculated from the generalized Brillouin zone, but we thought that it cannot be read just by looking at the shape of the generalized Brillouin zone. But later, when at a second thought, we realized that that's quite interesting. This shape of generalized Brillouin zone already contains the information about the PT symmetry breaking. The main result is that in the PT exact phase, the generalized Brillouin zone is a smooth curve. Here, this generalized Brillouin zone, which deviates from the unit circle, is a smooth curve, and the energy spectrum, the black dot, is all real valued, which means PT exact phase. But here, at this gamma value, at this non-Hermitian value, the GBZ develops a cut here, and this energy spectrum began to become complex valued. This is still real valued, but when the non-Hermitian parameter is above this value, and we can see clearly that the spectrum is complex valued, and there is two cuts in the generalized Brillouin zone, which is marked as blue. So there are 4 cuts in the generalized Brillouin zone. Here is this figure is about the transition point. So the cup, there is only 2 cuts here, and which is split into 4 as the non-Hermitian parameter further grows. So our calculation indicates that whenever there is a GBZ cut, we are in the PT symmetry breaking phase or at the transition point. So this is this result was quite surprising to us at when we first saw it. So but the reason is actually not quite complicated. The reason is rather simple to you will check this further. So you remember that we focus on a single band model. This is about this single band hopping model, and the Hamiltonian is just a number. So the energy spectrum is just the Hamiltonian itself, but with beta varying on the generalized Brillouin zone. We can split this beta into its absolute value and the phase factor. And this derivative dE d theta can be written in this way: partial h partial beta times this this expression in the bracket. So at the cut, the partial derivative of the modulus of beta with respect to the theta has a jump. So it jumps from one value to another value, and which means that this d theta, this derivative also has a jump. So in the spectrum, this jump in the derivative means that the spectral curve changes direction. So here it's horizontal, and here we have the vertical curve. So this jump in the derivative means that we have a branch point in the energy spectrum. This exactly means that there is a PT breaking. We have complex valued energy spectrum. So the result is that the PT symmetry beacon can indeed be seen from the shape of the generalized Brillouin zone. So we are preparing a manuscript on this result, which hopefully will appear very soon. And this is about one-dimensional problem. And with a few minutes, I will talk about briefly talk about the non-Bloch PT symmetry beyond the 1 dimension. So let's move to the 2 dimension. So we consider again we start from a very simple hopping model with non-reciprocal hopping k plus minus gamma along these 2 directions with the additional diagonal hopping s. So at first sight, the spectrum, the PT transition looks quite normal. As we increase the non-Hermitian parameter gamma, the imaginary part are real valued at first for small gamma and becomes complex valued for the large gamma. So this looks very normal. But what becomes strange is this. If we change the size of system, it looks very strange. For a very small size, for example, L equals to 10, and we have purely real eigenenergy. But for a larger size, this imaginary part becomes non-zero. For even larger size, the proportion of complex valued energy spectrum becomes even more. So this strong dependence of the size looks very strange. There is a PT breaking simply by increasing the size of the system. So to further investigate this problem, we can check the proportion of the complex valued energies, eigenenergy in this 2D-dimensional plot. We see that for whatever small gamma, the spectrum becomes complex valued as we increase the size. For example, if we start from a small gamma field, for the small size, the spectrum is real valued. But if we increase the size and we move toward the right direction, it becomes dark, means that there are many complex valued eigenenergy. So
Professor Zhong Wang, can you try to wrap up the talk? We are kind of out of time, so yeah.
Okay.
Sorry about
okay. Let me finish it as soon as possible. So we also compare this 2D result with the one-dimensional result. So for one-dimensional system, if we start from a very small non-Hermitian parameter, and we increase the size, nothing interesting happens. For very small size, of course, there is a finite size effect, but as the size increases to a certain value, it becomes independent of the size. So, but in 2 dimensions, the threshold, the PT breaking threshold, universally approach 0 as the size increase. And we have also looked at a 3D model, actually several 3D models, and the picture is very close to 2 dimensions. So our conclusion is that above 1 dimension, for 2, 3, 4, and even higher dimensions, the behavior of non-Bloch or PT symmetry breaking is very different from in 1D. And in higher dimensions, the threshold universally approach 0. But what is elusive is that we have not found this universal function. So we believe that there is a universal function which can tell us how the proportion of complex valued energy spectrum vary with the size, but this we have not succeeded in doing so. So this I think indicated that there are many interesting things that we have not understood. This is just one indication that there are interesting physics that we have not understood for non-Hermitian systems above 1 dimension. So this understanding behind this observed phenomena, but I think I just keep this slide. So a quick summary is that the combination of the PT symmetry, the non-Bloch band, give us this non-Bloch PT symmetry, and this is in one dimension. This non-Bloch PT symmetry is visible in the shape of the generalized Brillouin zone, and in two higher dimensions, it becomes more universal, and it's even more interesting. This could be observed in experiment, and also this is also very elusive, which have not fully understood, and it will be left for future studies. And with this, let me conclude my talk. So I would like to thank these collaborators. These four guys are my students, and these are my experiment collaborators, Wei Yi and Peng Xue. Okay, thank you.
Okay, thank you very much for a very interesting talk. So we may get some few questions from audience. We have question from Sonu.
So thank you for the nice talk. So I was wondering whether this non-Bloch topological invariant also tells about the exact number of boundary modes.
Yes, thank you for the question. Yes, it indeed can do so. Yes, when the number of edge modes are 2, then we have topological invariant equal to 2. Yeah, it's an integer. For this problem, it's an integer valued quantity, and it has a number of edge modes.
Okay, thank you.
Also, we had a question from Aris.
So have you ever seen this PT broken phase in this, say, when diagonalizing a Schrödinger type Hamiltonian?
Sorry, the question is, have we seen the PT breaking in a Schrödinger type evolution? You mean
Yes.
this is what we did is discrete time evolution, right? You mean you mean a continuous time version of this phenomena?
No. I mean that if you solve a Schrödinger type Hamiltonian where position is a continuous variable, so you're solving a differential equation instead of diagonalizing a Hamiltonian, a matrix Hamiltonian.
Oh yes, there are also examples with x continuous with in the continuum model. There's also such non-Bloch PT symmetry beauty.
So you showed in earlier slides a reference where a paper claims to prove that the spectrum is real if the Hamiltonian is PT symmetric. So are you claiming that that paper is incorrect?
Sorry, could you that question again?
Right. In an earlier slide, you showed a reference that claimed that the spectrum is real if the Hamiltonian is PT symmetric. So are you claiming that that paper is incorrect?
Not exactly. The PT symmetry means that the spectrum can have real valued eigenspectrums for provided that the non-Hermitian parameter is smaller than a threshold value. For example, this non-Hermitian parameter is smaller than the kappa here. But for very big non-Hermitian parameter, the threshold can still be complex valued. So PT symmetric Hamiltonian generally has two phase, the PT exact phase and then the PT broken phase. The spectrum is not always real value.
No, I understand, but in the previous slide, I think you have a reference to.
Which
yes.
This slide?
No, the next one, I think. Oh no, the previous slide. Sorry.
This one?
Go back again. Yes, this one. The title says
This one.
Yeah, real spectra in non-Hermitian Hamiltonians. Are you saying this paper is incorrect?
No. This paper is correct. No problem. Yeah, this paper is not incomplete with what I said, right?
So this paper is not
Yes,
claiming that.
it also has a PT symmetry, which means that the spectrum is real valued for certain parameter regime.
Aris and Zhong, so since we are a bit out of time, so probably we may postpone the discussion later, or maybe some personal discussions.
Yeah. Okay. Thank you, Zhong.
Yeah.
Thank you.
I also have many questions to ask, but we are a bit out of time, so I will ask you later if time is allowed. I want to thank again for the nice talk, Professor Zhong. Okay, so
thank you.